Okay, so welcome to my Corpuscle 2 video for the full A level for the last course, and I'm looking at Edexcel course. Now, I've got my order here that I'm going to go through, starting with hyperbolic functions and ending with coupled first order differential equations. Now, we'll start with hyperbolic functions because they're relatively easy. So we'll start off with the definitions of the hyperbolics, which is sin x. Now, sin x is a half of e to the x minus e to the minus x. And sin looks a little bit like a cubic. It is not a cubic though, from how you look at it. It looks a little bit like one if you squint, but it isn't. Just bleak out of that. For cos x, that's just 1/2 of e to the x plus e to the minus x. Remember, cos goes with a plus, sin goes with a minus in the middle. That's the only difference, isn't it? And with cos, it looks a little bit like a ternary sort of thing, and it goes through 1 there, okay? For tan x, that's just sin x over cos x, which is e to the x minus e to the minus x over e to the x plus e to the minus x, and you might see it multiplied through by e to the x. So e to the 2x minus 1 over e to the 2x plus 1, you might see it like that sometimes. It depends really. I'm not going to write out cosec, sec and cos because I've already got so much to memorise, and those are just relatively simple, it's just the inverses of those. I've rolled out our sin, our cos and our tan now, because these we're going to refer to a little bit later on, but one of these I want to refer to is this, why it doesn't have a minus in it. I'm going to put the minus in there, and it's because we take an extra minus when solving equations, and that is solely due to the symmetric weight of the curve of cos x. So cos x is 4, you're going to get a positive log and a negative log, aren't you? So you're going to get one of each, basically, it's common sense. And those are in the phone book as well, that's what FB means. If you see that later on in my videos, FB just means if it's in the phone book, I don't recommend that you remember it, okay? Identities then. They are virtually the same as the trigonometric. However, we have to remember to apply Osborne's rule. Now, it's any sign or implied signs, any implied sine squares rather. So any sine squares or implied sine squares are, importantly, negated from their trig identity. Meaning, it's, for example, cos squared x minus sin squared x equal 1. Not the classic Pythagorean where it's just sin squared plus cos squared is 1. Different from its trigonometric. That's all I'm talking about there. You could write it as minus sin squared plus cos squared, but I like writing it with my minus in the middle, not the front. That's just mathematical way that I do it. I like to do those things. Or you've got, for example, 1 minus tan squared x is sec x. Now then, looking at solving equations, for example, you've got 2 methods for this. You've got identities, then inverse functions, or my other method is the exponential forms, and then you solve the quadratic in e to the x. Okay? And you might want to load a substitution in there if you're not confident at spotting those quadratics. But really, we should be getting through with those now. So that is pretty much all your hyperbolic function stuff for the basic. We'll come back with differentiating them later on. So that is your hyperbolic functions. Alright, so on to complex numbers. Sorry about my voice, by the way. So we're going to check our Corpuscle 1 knowledge, make sure we know about that for complex numbers before we get to the exponential form of a complex number, where you've got z equals r e to the I theta. And e to the I theta is cos theta plus I sin theta. We know what that is from our Corpuscle 1 knowledge. Then we've got Dumbledore theorem. Now, Dumbledore's theorem I highly memorise, even though it's on the phone book. You start remembering it anyway. It's r to the n e to the n I theta. which we can obviously put in a more neater format using our cos theta plus I sine theta. So it's cos n theta plus I sine n theta. So we can just break that apart a little bit. So the application of the Laplace theorem, where you'll use it, is especially with application number 1, which is expressing in terms of trig powers. So we'll start with something like this. We're going to start with the Laplace theorem. That's nice and easy to do. We're going to do some binomial expansion on the left hand side, and the Laplace theorem you're going to get is cos theta plus I sine theta to the power of 6, aren't you? So I've got the power of 6 term there. Now that's going to be, using the Laplace theorem, cos 6 theta plus I sine 6 theta. So you're going to do as a binomial on the left hand side. Now a nice tip for this, instead of writing cos theta out all the time, bring a let in, bring a substitution, and let cos theta be C and sine theta be S. Otherwise you've got loads of cos thetas and sines going around that just gets messy. So you're going to compare your real parts, and the real parts you typically will compare with your cos 6 theta, and your imaginaries will go with a sine 6 theta there. Alright, then we compare both sides. And obviously we want to use our Pythagorean identity, sine squared plus cos squared is 1, there are range of that, and substitute that in where required. Some of the series one is really short here. We're just going to check our A2 pure formulae. So the sum to infinity is A over 1 minus R, make sure we know that. And then the sum from to n, which I don't know, it's in the formula, but I just remember the infinity one. I don't know why. Some extra identities then. So we've got Z plus 1 over Z is equal to 2 cos theta. I just start remembering these pretty quickly, and then they're just quite easy to remember from there. Well, I've got a minus. Now, minuses usually go with sines, and it does, it's 2I sine theta. So we've got Z to the n plus 1 over Z to the n, so just in terms of n now, would just be 2 cos n theta instead. And then I've got Z to the n minus 1 over Z to the n, well that's 2I sine n theta. Sine of n theta, because it looks like two n's next to each other there. For the last one, the second application of the Laplace theorem is when you've got something like sine to the 5 theta is 1/16 to 5 theta minus 5 to 6 sine 3 theta plus 5 8 sine theta. What I'm going to do is going to start with that because we know it's going to be in some form of this one up here, and you're going to get that equal to, remember the right way around, it's 2I sine of theta to the power of 5, that's right. Remembering how to do it. Binomial on the left hand side, and again it's pretty much the same thing. I'm going to reuse our identities as follows. There are a few more that I want to look at which are kind of like hyperbolic. They're not really, but they sort of are because they're using the e to the I, the e's and etc. So that was something nice. Then we just need to look at roots of unity and simplifying harder denominators than just doing things like 3 over 1 plus 4i and just memorising the complex conjugate theorem. Yeah, make it a bit more complicated in year 2. All that's good. Okay, so one of the last things we need to look at then is the rest of complex numbers, looking at roots of unity and etc. So let's get straight to it with the hyperbolic identities, or hyperbolic, not really. But we've got cos n theta and sine of n theta. Now these come in their own original forms, very similar to the original hyperbolics. Now they all have a half at the front, and that's very similar to the hyperbolic form, with e to the ni theta. Now cos goes with a plus, e to the minus ni theta. They look like hyperbolic forms, but they're not really. The sine one is a half of e to the ni theta minus e to the minus ni theta, of course. And then obviously you can rearrange them to get them into these two forms of 2 cos n theta, and this one, well, that'll be just 2 sine n theta. These are useful in this form more than in that form, so I highly recommend remembering those. So if we've got exponential denominators, all that means is in the denominator we don't have a nice simple one where we can just multiply by the complex conjugate. We need to multiply by something else. Now, the way I like to remember it is probably the way you were probably taught to do it, is we multiply by e to the negated half power. Now what I mean by that, by the negated half power, is I will multiply by e to the minus n over 2I theta. If I don't do that, I'm going to get terms that don't cancel, which isn't good. Now I wanted to go through this example here, which is 3 over e to the 5I theta plus 1. So I will multiply by the negated half power, e to the minus 5 over 2I theta, is what I would multiply through by there. And I can go ahead and do it now should you wish. But it's that negated bit from negative half power that's required in order to actually get through the question. Otherwise you're going to be stuck. So it's going to be 3e to the minus 5 over 2I theta. Now I have to be careful when I do my denominators, because I'm going to get e to the 5I theta times e to the minus 5 over 2. So it's 5 and minus 5 over 2, which is 5, which is e to the minus 3 over 2, isn't it? It's e to the 5 over 2I theta. Add e to the minus 5 over 2I theta, there we go, which is 3e to the minus 5 over 2I theta over, now that one looks like one of these forms, doesn't it? It's with the cos one, though, it's 2 cos of 5 over 2 theta. So I can just manipulate that how I wish on that one there. Alright, so that is a nice simple example there. I'm going to quickly touch on infinite series. So when we've got infinite series in cos and sine, we can convert them into the exponential form using these. We can use our formula for a of 1 minus half of the sums of the series. We can use that, and we can simplify using this technique and this technique, which I'm going to look at in a second, and we compare our real and imaginary parts, nice and simple. So the other form is, when it's in this form, c e to the ni theta plus or minus k, or k plus or minus c e to the ni theta, where c is not equal to 1 or k is not equal to 1. So what do we multiply by here? Well, we multiply by the same expression, but the change is we negate the power. Okay. What I mean by negating the power is to change the sign of it. So here I will multiply by e to the 4I theta minus 2 over e to the 4I theta minus 2, and they will end up cancelling each other out, and we can just go ahead and simplify that as you would. You could bring the minus up there actually, in fact we'll do that. We'll bring the minus up into the powers, and then they will cancel each other out, nice and simple. So you'd have that times that, so 3e to the minus 4I theta plus 6 over, well those two will just cancel each other out there, won't they? Just timesing them together. It'll be 1 plus 4, is it? So it'll be 5 of it. And then we got that times that together, which is plus, now it's a plus then a minus, so it's going to be cos again, it's going to be 4 cos of 4 theta. If you can't see that, make sure you go through the algebra and just work through multiplying those together. I don't need to go into those in much detail. Roots then, so if we're solving things of the form z to the power of n equals w, we form an exponential form for w. Well, I've done loads of exponential form. That'll just be a nice easy piece of cake. We raise it to the 1 over n power there, make sure you remember which one is which, and we put plus or minus 2 pi over n, plus or minus 2 pi k over n, right? to the power, ensuring we stay between our argument of minus pi and pi. If you don't, you're going to get a bit stuck, aren't you? So, the roots of a unity then, what do they form? Well, they form the vertices of an n-sided polygon. The sum of all of the roots is equal to 0. There's a little hack there, I quite like that one. If I multiply by w, it moves anti-clockwise to the next vertex. Vertex. And the last one, what if it's not at the origin? Well, we subtract the center so that it is. And then when you can go from there, you just perform your calculations and add it back on. Perform calculations. So you make sure you're no longer at the origin and you've moved to that correct point. Because really, when you're at the origin, it's quite simple to do. So you do that bit with the origin and then you move back. That's what you do. And I think I've covered everything there for complex numbers. So all the rest to do is just series, method differences, more interesting differential equations to go as well. Hope you enjoyed that and I hope that helped. So now we'll look at method of differences in the Maclaurin series. So when do we use the method of differences? Well, when it's in the form f of n minus f of n plus 1. Or the other time we can use it is when it's f of n minus f of n minus 2 is the other form, plus 2 rather, I should say. That's the other time we can use the method of differences, when it's in either of those forms with a sigma, of course. It's all to do with the sigma. Okay, make sure you can join capital sigma as well. The Maclaurin series, it's the formula for it you can find in the formula booklet, and it's f of 0 plus f dash 0x, and then you can work out what's going on. It's going to be f double dash of 0x squared over 2 factorial, and you can spot the pattern. It's going to continue over and on forever and ever, up to how many terms you wish. With x cubed, it'll be the triple derivatives, and you just keep taking derivatives, don't you? And like I wrote here, there's lots of many useful standard results in the formula booklet as well. So this is when your formula booklet is your friend, basically. For a compound function, however, I've got logarithms. Now, I don't really want to deal with that right now. So what I'm going to do is I'm going to break that into the natural log of 1 minus 3x, but I'm dividing, so I'm minus the logs, and I can bring the half out the front. So this is just a power of a half, isn't it? Like, we'd normally just expand it just the natural log of 1 plus 5x. And then I can expand each of those terms, and then take one away from the other. I can do that as well. That is your basic series knowledge that you need for Calculus 2. Next up is polar coordinates. Okay, so now we're on to polar coordinates. Now, for polar coordinates, we've got the facts we need to remember. X is r cos theta, y is r sin theta. Now, if we go back to our old favourite of the Pythagorean identity, we can say that r squared is equal to x squared over y squared. In Edexcel, all the questions we have to deal with are where r is positive, where r is greater than or equal to 0. R is never 0 half the time. The one from the form book for area. Now, I highly suggest you memorise this because it comes up a lot, is a half of the integral of r squared d theta between alpha and beta. Now, alpha and beta are your limits. However, you have to be careful with your limits because your areas are not horizontal anymore. Your areas go at an angle. Your areas from here will go to here. They're on that sort of slopey angle, if you see what I mean. Now, you do need to rearrange 4 and 3 double angles, So I'll go ahead and just derive these for you nice and quickly. So we've got the cos 2 theta, cos squared theta rather, minus sine squared theta. Now, I want sine squared, so I need to eliminate the cos squared, so it's 1 minus sine squared theta minus sine squared theta. So it's 1 minus 2 sine squared theta, cos 2 theta. Now I want sine squared, so I'm going to add that to there, so it's 1 minus cos 2 theta equals 2 sine squared theta. Divide everything by 2, so it's just a half minus a half cos 2 theta. So half minus half cos 2 theta for sine. Now if I want cos, I'm going to come back to the original one and do cos squared theta minus. We've got a bracket in, so I don't make a mistake here. So I'm going to do 1 minus cos squared, isn't it? Now I've got cos squared theta minus 1 double negative, so it's going to be 2 cos squared theta minus 1. Just being careful of which way around you do it. Now I want cos squared, so I have to add 1 divided by 2. I'm going to get cos squared theta being a half cos 2 theta add a half. Or a half plus a half cos 2 theta, that way. Just so you can recognise which one goes with a sign, a negative and a positive. And remember, sine goes with a negative, cos goes with a plus. Went back to sine and cos. Sine goes with a negative, cos goes with a plus. Yeah, you can see these patterns. For tangent, something to remember, if it's a horizontal tangent, so like that, or a vertical one like that. For horizontal, we know that dy by d theta must be equal to 0. That's always useful to remember. And for a vertical one, it does the opposite, it's dx by d theta. Must be 0. Not theta, 0. Because you're going to end up with parametric equations and theta, aren't you? That's what these are. These are basically parametric equations. So for parametric differentiation, if you wanted to convert from Cartesian back to polar, for example, all you need to do is make one the subject to the other and substitute back in, wouldn't you? So this is just a little bit of an extension of parametric equations with some nice integrals within them. Alright, so that is block 1. Okay, so now on to another huge topic of further calculus, which includes all your differential equations and stuff later on. Okay, that's what that whole list is for, by the way. That's just a walk through the order I'm going through them, so if you want to skip to a certain bit, you can do that. Okay, so improper integrals then. It's improper. Now, this is kind of sneaky, or if one or both bits if I put it R plus minus infinity, that will do. Or if undefined, if I get there, at any point of the integral, so you can't evaluate infinity, for example, or you can't evaluate when things are divided by 0, obviously, because you can be extended up to plus minus infinity, etc. So we use limits instead of that. So I like to say the limit as a tends to infinity of the integral between 0 and a of e to the minus x. Now everyone can do that in any different way you wish. I like doing it that way, and then I just evaluate it there. If it will converge or diverge from the solution, you can work from there how you wish. It's always worth drawing the graph as well, if you can get some good graphs, get some skills in there. Mean value theorem is 1 over b minus a of the integral of a and b of f of x dx. I just get learning that, and then you just apply it how you wish. For the mean of f of x plus k, it's f bar plus k. Remember, I'm using f bar or y bar. Again, it doesn't really matter so much. For kf of x, it's just k f bar. It just follows the same rule there. Nothing too much different. And then we're on to, after the improper integrals and mean value theorem, we've got the whole list of standard results that we need to remember. This is going to be a long one. We're in for a long ride here. That's going to come next. Okay, so these are all the derivatives that you remember. Now, most of these are given to you in the formula booklet. This is why I say it's highly recommended that you use the formula book for this, like I've said down here. But the one thing I will let you know, a little secret on, is these here. The reciprocal of the hyperbolic forms. Now, you're not entirely, you can't see it on the spec. I've had a look. You can't tell if they're on the spec or not. I'm going to stick them in here because they're quite good to remember. Because this is just minus cosec x. That one changes from its original. And that one's the same. It's shec that changes. The shec has a minus, not a plus. It's minus shec x 5. And then cof is the same. It's just minus shec squared. Alright. Is it minus cof squared rather? Honestly. At this point in the day you've filmed so much, you do make all errors. But yeah, it's these that I highly suggest that you learn. Because they're not in the spec, but they're worth knowing anyway because they could throw them in. These are in the formula booklet, some of those, to be honest, you can probably worth remembering them, and those are as well. So, as I've got down here, it's only these are the stars that change, so only cos x and sec x change from their standard trigonometric forms. And of course, these give your integral facts. If you see an integral of that form, you know it's going to go to some R shine. If you see the integral of that, you probably know it's going to be some form of R cos. You'll probably have to do some scaling maybe. If you don't know what I mean by scaling, make sure you go and watch the integration playlist, which is currently in the midst of going. It's a long one, that one. The integration playlist for L maths and not for further. For further, I've already done videos on the inverse trigonometric integrals. This is stuff I've already done. We're pretty much there now. I just need to finish off second order differential equations, looking at how you couple them together with first orders and all that stuff. Okay, so that is your big section of derivatives. Okay, so now on to integration, as you could have probably expected. So we've got each of these functions, f of x, the integrals of them are given here. I just wrote these out because they're in the formula book, there's no worth just me writing them in, other than the formula book anyway. But yeah, you've got the inverse trigs for hyperbolic and non-hyperbolic forms, and then you've got some standard logarithmic results which are quite nice to prove if you want something to do. Now, any of these can be replaced by x plus k all squared. Now, the way to do it is to change the x to x plus k in the standard result. The way the textbook likes to do it is a long-winded substitution. Why bother? Just change x to x plus k and move on. So, sensible and appropriate substitutions. When it says to use appropriate substitution to find this integral, what's my substitution going to be? Well, if I look at this, I'm thinking, okay, let's have a look at the formula book. I'll look at the formula book. Which one do I see that corresponds with it? Oh, the sign one look a bit like it. Oh, it is like it. Okay. So I'm looking at that. What's my substitution going to be? Well, I probably want to say that's a sine of u. Doesn't really matter. It doesn't have to be u. It could be anything, to be honest. It doesn't really matter. And then for the second one, I've got the integral of 1 over the square root of a squared plus x squared. Well, that's like it's going to be something to do with our shine. So it's going to be a shine u. Then you go through the appropriate method of integration by substitution. Now, partial fractions are covered in the A-level maths course. However, there's some little tweaks here and there, looking at things where they're improper, where you've got repeated factors in there, and you've got some non-linear factors in there as well. Now, the way to do this is a little bit more sneaky, so bear with me. I've got to deal with it all in this question. So, I have x to the 6 plus 3 over x times x squared plus 2 squared. Now, the first thing we're having is we divide these out. Now, I see when I get x to the 4 terms, so when I divide them by each other, I'm going to get a linear term of x plus b. Now, if you can't see what's coming from, go through the argument. Then I'm going to get a plus c over this term here for the x. But I'm also going to get, being careful, a dx plus 2 over this x squared plus 2 But I'm not finished, I need to deal with the squared bit as well. So I'm going to get x equals g over x squared plus 2 squared. To deal with, remember that sponge I talked about in a previous video on partial fractions? Yeah, that sponge to essentially soak up all that extra bit. So that's what's happening with partial fraction. If you can't spot that, go through the algebra and divide through if you want. Just go ahead and use the algebra. That's all I can say for that. Just go ahead and use your algebra. Now, if you see x squared plus bx plus c in the denominator, so things like 1 over 2x squared plus 4x plus 7, for example, you're going to find the integral of that. What you're going to do is on the denominator, you're going to complete the square, you're going to get it into one of these forms, and you can probably find it some sort of trigonometric form when you break it all apart. So 2x squared plus x plus 4x plus 4, you factor the 2 out, and then you factor the x out of 2 terms, and go ahead away and do as you will complete the square. Whew. Right, next, differential equations. This is the stuff you might need my help on, because differential equations are a little bit tricky now. Almost just kind of like tickle the water with a separate variable, which is where we'll start, and then we'll get meaty into some other hard differential equations. So, that's coming next. Okay, so, first order differential equations is my favourite. So, in LMS we started with separation of variables, didn't we? And we said that we could use this dy by dx as a fraction. So, I could do 1 over the function g of y dy equals f of x dx. And I could integrate both sides. That's fundamentally what we do, something like that. For this one, I've got x cubed dy by dx plus 3x squared y plus sin x, which is a reverse product rule. Now the reverse of the product rule will tell me that this is just a derivative of a product. And the product is x cubed y equals sin x. Now to get rid of the derivative, I just integrate both sides like normal. I just get x cubed y is the integral of sin x. I look ahead from there. An integrating factor, it must be in dy by dx plus px times y equals qx. So px and qx are functions of x. The integrating factor is e to the power of the integral of the function p of x in respect to x. I just learned that, and you just go ahead and do it. And then you multiply through by the integrating factor. That's how you solve it. Done. Now, harmonic motion. So we know that the acceleration is dv by dt. Now, we have an alternate form for it. Now, if you remember it, I remember it as v dx by dt. I don't know if you like remembering it that way. Well, damn it, no. V. No. That's the way I remember it. I just remember to go back in my brain to work out how to do it. But it's similar to, what's it called? Product rule, pretty much. For x equals a sine of omega t plus alpha. So when we're seeing anything in that form, we need to make sure we know which is which. So the amplitude of the curve is a, which is the coefficient. That's how high it goes for amplitude talking about. And then for the period of the function, it is, now, I believe it is lambda alpha over omega. That might look a little bit crazy to you guys, but yeah, that's it. And then for forced harmonic motion, we've got x double dot plus x plus kx dot plus omega squared must be equal to a function of t. And then we go ahead and solve that. That's one of those where if you don't know it, you don't know it. But yeah, forced harmonic motion. And then you go look at damped harmonic motion next. When we're looking at types of damping, etc. When we're looking at second order differential equations, which is next. So we've got second, and we've got coupled to look at, and then that'll be the end of this video. So yes, second order differential equations up next. Okay, second order differential equations then. So, they're always in the form a double prime y plus by prime cy equals a function of x. More than likely it will be equal to a function of x. If they're not, then they're homogeneous and they're not equal to f of x. If they do have an f of x, they are non-homogeneous and we need to use particular integrals in order to solve them. So, our general solution mainly is formed of the complementary function plus the particular integral. I always remember that form and we write it down immediately. The auxiliary equation, I like using m, am squared plus bm plus c equals 0. You should be able to find the roots to a quadratic equation. You can just go straight on your calculator if you wish to do it that way. So if I'm looking at two reals, now I'm going to use alpha and beta because I quite like my Greek letters. I'm going to go ahead and use those for the real one, you don't have to. So it's ae to the alpha x plus be to the beta x. And then we just use that form every single time. For one real repeated, it's a plus bx. Now I'm just going to pick alpha because I don't really bother which one I want to use. We just e to the alpha x. Again, just remember these forms and you will be right as rain when you get through these. For two imaginaries, it's a cos qx plus b sine qx. And then for two complex solutions, I'll use p and q, why not? It's e to the px of a cos qx plus b sine qx. Now, if they're harmonic or not, this is quite unusual. The two complex ones are very much light damping. Now, the two imaginaries are formed in simple harmonic motion, or SHM for short. If you want to remember it that way, feel free to. Like I say, some people quite like doing it using SHM. I don't mind it. The only problem I will say with harmonic motion is people forget which one it is. I think it's just being aware, really. Yeah, there's not much you can say, is there? Really just being aware. For harmonic, especially for the two reals, it's heavy damping. For the one reel repeated, it is critical damping. Remember the difference. It's important because you could be asked it. And if you don't know, he's like, well, I'm a bit stuck here, I don't know what I'm doing. Particular integrals. Now, for a particular integral, it's just of any form, not really bothered which form we're using. Now, the forms you're going to use for if it's just a constant at the end, you're just going to use lambda. I quite like my Greek letters, I'm going to stick with them. For x plus b, you're going to use mu x plus lambda. You can probably see the pattern here. I'm going to use vx squared plus mu x plus lambda. And again, I just remember these forms. This one will leave us lambda e to the px. This one, you could just guess it is lambda x e to the px, but I need to make sure I add lambda of mu x e to the px to make sure. Mu rather. Making sure I get that extra bit once again. This one is lambda cos qx plus, now I've got a different constant here, which means I have a different number at the end. I'm going to use mu sine qx, doesn't matter. Those are particular integrals. So there are some exceptions to the rule where your right hand side will have part of your complementary function that you initially found from your auxiliary equation. Well, what do I do here? Well, you multiply through your particular integral by x or x squared. So if I had it for this one, for example, I can multiply that by x. See what I mean? I've done loads of examples already on those, so just go ahead and look and watch the video on that. The method then, so what am I doing with all of this? What's the method? Well, the method in general is I differentiate my particular integral that I'm setting twice. Then you're going to, as you can probably guess, summon it back into your original differential equation that you've been given. Once you've done that, you're going to solve for these constants that you initially found of v, lambda and mu, and then you join it to give your complementary function and you have your general solution. Your particular solution, just like you've done for LL maths, you just sub in boundary conditions and you can find all your constants for everything like a and b, etc. There's many methods you can do that, but I just quite like this method because it's very regimented and you just learn it. So this is it. This is the end of this at the minute for second order. I've just got a couple left to teach you, and then when you remember the couple method, that's it. So, not much to go. So the last bit really is looking at coupled first order differential equations. Now I've just made these up off the top of my head. I've got dx by dt being ax plus by plus a function of t, and dy by dt being cx plus dy plus g of t, where f of t and g of t are different functions of t. So the method for this is I like to make y the subject in the first equation. Now that's not hard to do, really, is it? I just take that over there and divide through by the constant. Reasonably easy. I then, when I got y equals, I find y dot. Now y dot is the same as saying dy by dt. Differentiating. That's all that is. I sub into equation number 2, which is this one here. And then I'm going to put those equal to each other. I'm going to get a second order differential equation in x. I've just done second order differential equations, which will be nice and easy. I solve that second order differential equation like I would if we're doing it normally for x. And then I get x equals, I differentiate that x dot. So x dot is literally just dx by dt. And I'm going to sub that one back into equation 1 and I'm going to rearrange to find my equation of y, which is therefore my solution. Okay, so essentially subbing that back into here. So it's a cycle, it's coupled. Coupled, or I can call it a system of differential equations if you wish, because it is basically advanced simultaneous equations. I don't know what it is. A bit like the simplex algorithm. So, this is the end of my video. Thank you very much for watching this. I know it's a long one. Right, so what next? Further mechanics? Or do we go into decision marks maybe? Let me know what you want. I can see how much I can get through in year 13, of course, because this could be quite a tricky year, because I think the hardest bit on this is the complex numbers and possibly polar coordinates, because they are quite sneaky with the questions they can throw in on those. Being aware, isn't it, of course. So, and then I will get back to the exam papers, of course, as well. Okay. Thank you very much for watching, and I'll see you all in the next video. That's why now out of here. Bye for now.